this video, we're going to practice working with transient energy balances by working on problem 4 of the Chapter 10 Lecture Problems worksheet. The premise for this problem is that we have some sort of batch reactor that's wrapped in an electric heating mantle, and this batch reactor is filled with a liquid. The contents of the batch reactor must be heated from 25 to 250 degrees Celsius before any sort of reaction can take place. And so based on the data given here in this table, the problem asks us to figure out how long does it take to heat the contents of the reactor from 25 to 250 degrees Celsius. So based on the information in this problem statement, I want you to use it to develop a process flow diagram. Pause the video here and do that. Using the information in this problem statement, we could develop a process flow diagram that looks like the one here. It essentially looks like the other process flow diagrams that we were using for batch reactors when we were dealing with the material balance. But now we're only dealing with the energy balance of the system. In any case, in this process flow diagram, what we have is a batch reactor that's well stirred, so there's an impeller here. And over time, there's some sort of heat rate that's being added to the system. Okay? We're given the mass of the contents in the reactor along with its constant volume heat capacity. And we're also given the mass of the reactor itself, so the actual, metal vessel, along with the heat capacity of that vessel. We're told that at some initial time, the contents are, at 25 degrees Celsius. And then the problem asks us to figure out, at some time final, how long does it take to get the contents to 250 degrees Celsius. So to figure out what this T final is, what we want is a relationship between the temperature of the entire system and also the time of the system. Alright? So to approach this problem, rather than jumping directly into deriving the energy balance, what I want to first do is I want to simplify the system, because basically the system is composed of two parts: the reactants or the contents inside the batch reactor, and then also the vessel itself. So what I'm going to do here, in order to just kind of think about the problem as, being one component rather than two different components, I'm actually going to calculate some average properties, right? Specifically, I'm going to calculate an average heat capacity for the system. So a CV average. And the way I'm going to calculate that is I'm going to assume that the average heat capacity is just a weighted average of the heat capacities of each of the individual components. So the reactor contents and the vessel itself. So to calculate CV average, I'm going to calculate the mass fraction of the reactor contents, so 1.5 kilograms over 4.5 kilograms, which is the total mass of stuff in our system. So the reactor contents plus the mass of the vessel, times the heat capacity of the reactor contents. And then I add on the weight fraction of the vessel itself times the heat capacity of the vessel. So by taking this weighted average, I get a CV average of 0.38 calories per gram per Celsius. Okay? So this will help us simplify the energy balance coming up. In any case, what the problem asks us to solve for is how long it takes to heat the system up to 250 degrees Celsius. So essentially we want to figure out what T final is. To do that, we're going to develop an equation that describes temperature. Oh, I forgot the word describe here. to describe temperature as a function of time. So lowercase t. To do this, let's start with our general form of the energy balance. And our general form is our accumulation is equal to input and an output. For our accumulation term, we're going to say it's a change or the derivative of the total system energy. And that total system energy is made up of three different contributions, which is the derivative of the internal energy, the derivative of the kinetic energy, and the derivative of the potential energy. For the input and the output, that's equal to the heating rate plus the work rate. At this point, we can make some simplifying assumptions. So for this problem, we're going to assume that any changes in kinetic energy or potential energy of the system are negligible, and that the stirring of the liquid contents relative to the amount of heat that's added to the system, that shaft work is going to be negligible. So we're going to say that's 0 as well. And we also don't have any sort of reactions going on as well, so yet, because we're just heating the system from 25 to 250. So with all that, we could just say that the work rate for the system is about 0. So what we're left with is du dt. And at this point, I'm going to simplify du dt further and rewrite it as the product of the total mass times the specific internal energy of the system. This term is constant, right? Mass is conserved, so that won't change. So we can pull that out of the derivative. And if we're seeing as how the constant volume heat capacities we were given, those are constants as well, we could rewrite our specific internal energy in this form. And so based on that, when we take the derivative and then pull out all the things that are constant, what we get is CV, and call this a CV average, times the derivative of temperature with respect to time. So that's everything on the left hand side, and on the right hand side we just have our heating rate. Alright, so at this point, now that we have our differential equation that we want to solve, what we need to do is solve it so that we have an equation for t. So at this point, what I want you to do is to pause the video and think about how we're going to solve this differential equation. To solve this differential equation, I'll start writing it on the next page. But before we solve it outright, I'm just going to rearrange it a little bit. So on this next page, I'm going to rewrite it. And I'll write in such a way that we only have dt dt on the left-hand side. And on the right-hand side, we have q dot over m total and the heat capacity. Okay? Now in this form, you could probably recognize that our differential equation is separable. And so when I say that, that means we could describe our differential equation as the product of a function that depends on temperature and another function that depends on time. In our case, what we could say is that our g of t function is all this stuff here, all the stuff on the right hand side. And our f of t function is just 1. And so things here are quite simple. And so what we should do now is then move all the temperature stuff to the left hand side and all the time stuff to the right hand side. So what we have is just d capital T is equal to q dot m total CV times d lowercase t. Once we have that, we could then integrate. So we'll integrate d capital T on the left hand side, and then we'll integrate the lowercase t stuff on the right hand side. This is a fairly simple integral because this term right here is just a constant. And so if we integrate it indefinitely, what we get is t is equal to q dot m total CV times time. And because we integrated it indefinitely, we also have to worry about an integration constant. And so our equation's fairly simple so far. But what we have to do is we need to figure out how to solve for this unknown constant. So pause the video here and think about how we're going to solve for this constant. To solve for theta naught, to get theta naught, what we need to do is we need to apply our initial conditions for the system. And so for this system, I'll write it out here, our initial condition is that the temperature of the system is equal to 25 degrees Celsius at time is equal to 0. Okay? So let's apply this initial condition so that we can solve for theta naught. So t at t is equal to 0, that's 25 degrees C. And just to keep everything in symbolic, I'm going to call this t naught. So t naught is equal to q m total CV times 0 plus theta naught. So the stuff multiplied by 0, that whole term goes to 0. And so what we're left with is that our theta naught is equal to t naught, which is 25 degrees C. Let's now plug in what we solved for. So now we have t, just some general t at some arbitrary time, is equal to a time term plus an initial temperature, t naught. So this is a very simple equation, but let's make sure that it actually describes the system that we're looking at. So here, pause the video and think about how we're going to make sure that this equation is consistent with the behavior of our system. To make sure that our equation accurately describes our system, what we should check to see is that it satisfies both the initial condition and also the derivative or the differential equation that we started with. So let's first check to see if it satisfies the initial condition. So at time is equal to 0, if we plug in t is equal to 0 in our equation, what we get is we multiply this first term by 0, and then we add on t naught. And so what we're left with is just t naught. So it satisfies our initial condition. Let's now check to see if it satisfies the differential equation we started with. So if we take a derivative of our temperature equation, what we're left with is just q dot divided by total mass and CV. And so that also satisfies the differential equation that we started with. And so our temperature equation seems to be accurate. So I'll box that in here. Okay? But ultimately, the problem didn't just want us to derive an equation for temperature. It wanted us to solve, actually, for the time it takes for the system to heat up to 250 degrees Celsius. And so to do that, to get this T final, what we should do is plug in 250 as our temperature, and then solve the equation for that T final. Alright? So let's do it like this. T at some T final is equal to 250 degrees Celsius, which is equal to, according to our equation, the Q dot over M total CV times some T final plus T naught, which was 25 degrees Celsius. So if we rearrange the equation, we could solve for T final here. Alright? And so what we get, if I do the unit analysis, is 250 degrees Celsius, that T final, minus the T initial, 25 degrees Celsius, multiplied by the total mass of the system, which I'll write in units of grams, not kilograms, so grams here, multiplied by the average constant volume heat capacity, 0.38 cals per gram per Celsius. Okay. And the heat rate as well, which was 500 watts, or otherwise known as 500 joules per second. And then, I'll also convert at least the joules per second into a calories per second. 4.18 joules per calorie. And so the units, so the Celsius here cancel out with that Celsius, grams here cancel out with the grams, calories cancel out with the calories, and the joules cancel out with the joules. And so for a T final, what we're left with is 3,220 seconds. And I'm going to convert this to minutes because it'll give us at least a bit more of a perspective of how long that is. So when we convert it to minutes, we see that in order to heat our system from 25 to 250 degrees Celsius, it takes a total of 53.7 minutes, or basically an hour to do that. The last thing I want to do in this video is, now that we have this equation that describes temperature as a function of time, and we also know how long it takes to heat our system to 250 degrees Celsius, what I want to do is actually, plot the behavior, so that we get an idea of, if we wanted to heat the system to any temperature that we wanted, we could figure out how long that would take. So once again, I'm going to write the equation for temperature that we derived. So Q dot over M total CV times time plus some T naught. And if we inspect this equation, we'll notice that it basically has the form of a linear equation, right? Where this Q dot over M total CV is a slope, and this thing here is our intercept. And so when we plot our equation, we could use all the limits that we calculated, both the temperature at time 0 and the temperature at time final. We could use that to trace out the behavior of this plot. So in this sketch, the y-axis is temperature in Celsius. The x-axis is time in minutes. I'm going to mark off a value of 25 there, and a value of 250 here. Right? And on the x-axis, let me move this here. On the x-axis, the left side is going to be 0, and the mark I put here is going to be that 53.7 minutes, the T final. All right? And so what we know is that T is equal to 0, our temperature is equal to 25, and at T is equal to 53.7 minutes, our temperature is 250. And based on the form of our equation, we know that it's just a straight line. It's linear. So we can just draw a straight line between these 2 points. And we know that the slope here is equal to Q dot over M total and CV. And really, the last thing I want to point out here is if you knew, for instance, if you knew the total mass of your system, and you also knew the heat rate that you applied to your system, you could use those pieces of information and also the change in temperature to figure out what your average heat capacity of your system was. And so this is actually how people solved or measured the heat capacity of various chemical species. This is the sort of experiment that they would do.